To our example. So we are looking at a data set that is involving the mating patterns of elephants. And so apparently in the elephant population, there's a competition for females between young and old males. And males continue to grow throughout their lives. And so older elephants are going to be larger. And so they should have a more successful probability of mating. So the variables that we're going to look at are the outcome. It's going to be a count of the number of mates that a male elephant is able to successfully have. The covariates that we're going to look at are the age of the male elephant in years. Now, again, always, I cannot stress this enough, please always look at your data descriptively to try to see what is the best modeling procedure that you should use. Now, we can see that as we have low number, or a younger elephant, the count, the number of mates is lower, and as we increase the age of male elephants, the number of mates tends to be higher. Moreover, there seems to be much greater variability in the number of mates as age increases, which is something that we are assuming to happen again with a Poisson model, because that parameter lambda, the mean, is tied to the variation. So as we increase our age, as we increase the mean outcome here, as we increase the mean number of mates, we should be increasing the variation as well. And I think we have decent evidence of that, because elephants of age 30 pretty much have 0 to 4 mates, and then elephants of age 45 have approximately between 0 and 9 mates. So if the dispersion around the mean for the count response goes up as the mean increases, then we may be convinced that Poisson is going to be a good modeling choice for us. And again, that is because the variance is tied to the mean here. So when we look at the linear transformation of our outcome, we are taking the log of the expected value of y, aka the parameter lambda, and that is going to be equal to the linear associations that we estimate with beta multiplied by the value of x. So enough chit chat, let's actually get to estimating this model in R. So again, since we are using a generalized linear model, we're going to use GLM as the function. The number of mates is our outcome, and we are only using age in years as our predictor. The data is coming from the dataset elephant, and again, family is equal to Poisson. So, like any other linear model, we get back our estimated betas. That includes our estimated intercept as well as the estimated association between age in years and the log of the expected value of y. So if we're going to interpret these coefficients, we're going to need to do some sort of transformation, right? And that would include taking the exponent. So in this slide, what I want to do is I want to actually look at the expected value conditional on a certain value of our covariate. So what we're going to do is we're going to plot our fitted line. We're going to do that by taking our coefficients. So that's what I'm doing in line 1. We are then just setting up x values to plot along our x-axis. So here I'm just sorting all of the different values that we have for age. Then I'm taking the expected value here for all of those x values. So when I take coefs 1, I'm taking the intercept. And then with coefs 2, I'm taking the beta 1 estimate multiplied by what that x value is. And in order to get the linear transformation, I am taking the exponent of that. With lines, I am then just plotting the fitted line for different values of x. So what we can see is that the Poisson regression is a non-linear model for the expected number of mates conditional on a given value for age. Now, if we thought that this was a linear association, right, then we would probably be more convinced to use a least squared model.